today we're going to do the PD25 and PD50. We'll focus mostly on the PD25, and then we'll do a little bit with the PD50. And we consider that an all-purpose utility meter just because it does so many different functions. So we'll go over pretty much all of those functions today with the exception of one. And I'll point to that when we get there. But for the most part, we'll go over all the functions of the tool, and you'll see exactly how useful the tool is, not just in telling you if something's hot or not or phasing, but actually in troubleshooting. So it's a very unique tool that you can use it to troubleshoot a lot of your problems you may have on primary voltages. And what we have here is a list of all the different things that a PD25 and PD50 will accomplish. So if you look at number one here, it can be used as a traditional phasing meter. So in other words, just like the phasing meter that you may be using now that is not a PD25, you're using it to measure the difference of potential maybe across a switch, whatever the case may be. And you want to see a zero or near zero if you're in phase, some potential when you're out of phase. You can use a PD25 and a PD50 for that exact same reason. The difference is it's going to be a true RMS display. So if you notice on number 2 here on the list, this is a true RMS meter. In other words, if you're used to using a multimeter, like a fluke multimeter, it says true RMS on that meter. Okay, this is a true RMS meter as well. So in other words, it's a high voltage fluke meter. You can think of it like that. In other words, I can use it on secondary potentials or primary potentials, and a reading is going to be within 1% in the field. Okay, so commercial industrial voltage meter. So a lot of C&I customers that you may have voltages that's in a little bit of a gray area. So as an example, 4160, that voltage is actually hard for a traditional phasing meter to display that voltage, because usually on the lower end of scale, it becomes very inaccurate and it tends to want to show zero even if the voltage is not zero. So all those C&I customers, the lower voltages, the 2 kV, the 4160, this tool works remarkably well because you can distinguish those potentials really easy and extremely accurate. A phasing meter, for measuring secondary voltages. Again, since it is a true RMS meter, I can use it on 12208, which we'll demonstrate here. We have some 3-phase here in our training yard. Your 277 480, your 600 volts, any type potentials where, again, traditionally that phasing meter could not handle that. The PD25 has no problem accomplishing that task. A highline resistive voltmeter. So we do have some utilities that request this tool to be used where they have the interconnect cable attached to it, and we have this set up here, and we'll demonstrate that in a few minutes. But we have an interconnect cable attached to it with a ground clamp attached, and they just walk around with a 100-foot cable and they take readings. Okay, so that's a highline resistive voltmeter. You're not really utilizing the second probe. This cable just goes straight to ground. So again, it's a true RMS reading, but you're not utilizing that second probe. So we'll go over the pros and cons with doing that in just a few minutes, but you can use the tool for that task as well. The high frequency meter. So up to 400 Hertz, this tool. We're aware of some Navy yards are using this tool on their ships with the high frequency. So that is the only number that I can't accomplish in today's demonstrations. But again, you can use it as a high frequency tool. A DC voltmeter, we can demonstrate that. We actually have a 100-volt power supply here that we use as an accessory with this tool. So we can actually measure that 100 volts. You can measure the truck battery, that you have. Maybe in a substation, you have some battery backup. You can measure those batteries. Again, you can measure it on AC or DC up to 25 kV. So either or, doesn't matter. Capacitive test point phasing. We have some capacitive test points in our 3-phase cabinet to my left, and we can actually demonstrate using that tool specifically for capacitive test point phasing. And again, I'll just kind of reiterate here, since this tool is extremely accurate, you can actually determine if the capacitive test point is good or bad before you actually phase. We actually have another three-phase pad mount in here where one of the elastomold capacitive test points has gone bad. It's not in this cabinet, it's in another cabinet, but we've actually determined that it's gone bad. So again, you want to be able to test each capacitive test point, make sure it's good, phase to ground, and then compare that phase to ground on your other capacitive test points, make sure they're all good, and then you can go phase to phase and determine what's in phase and what's out of phase. A line regulator neutral detector. Again, with the accuracy of this tool, if a regulator is out of step, maybe the dial has broke. It is a mechanical feature of a regulator, so those things can fail. So you know, you can actually determine if a regulator is in step or out of step, you know, versus what the light on it may say. We actually have a Cooper regulator here in our training yard that's attached to our line coming in, and we can, you know, go in step or out of step and determine if it's accurate versus what it tells us. So again, with the accuracy of this tool, you know, if it's a 5/8 per step, you know, around 45 volts per step, thereabouts, you can actually see that with this tool. A phase sequence rotation meter. So again, if you'll notice, a lot of these numbers that I'm going through here, this whole list is single-use devices. So keep that in mind as I'm going through this. You know, a phase sequence rotation meter, that's a single-use device. And we have a little asterisk here, meaning that it does require an adapter, and I'll show you that adapter that you have to use in conjunction with this tool. But, you know, again, just keep in mind that a lot of these are single-use devices that you can do with one tool, with an accessory. But a phase rotation meter, you know, a lot of times a meter tells you if it's clockwise or counterclockwise, and we'll demonstrate here in just a few minutes how this tool can be used as a phase sequence meter. Now, an extremely nice feature about that is I can do that on primary. So if you think about that, normally you have to ride the line and find a three-phase secondary tap to determine the sequence, and then, you know, correlate that with your primary. Where I don't have to ride the line, I can determine my sequence on the primary. Or again, if you want to do it on secondaries, you can do it on secondaries just like you utilize your tool now. So again, extremely useful, saves a lot of time. A high pot tester. So this tool can be used to high pot primary cables. A lot of times traditional phasing meters are used in that capacity. So you just have a high pot adapter you thread on the end of this tool. And what's nice about this tool, again, with the accuracy, is I can actually test the high pot. So again, that's a single-use device with a lot of manufacturers. I can test the high pot phase to ground, make sure the high pot is working. You should get about roughly 70% of your phase to ground potential on your display. And then I can high pot that primary cable. With the accuracy of this tool, for every microamp of leakage on that cable, it will be displayed as 50 volts on this display. So I can actually determine how much leakage I have on that primary cable by what the display tells me. So again, with the accuracy built into this tool, it gives you much more information. You can determine if the cable is going bad, it's getting old, maybe it's a really long cable, so it inherently has more leakage on that cable. You'll see that on the display. A high pot URD cable, we just talked about that. A DC leakage tester. So as far as testing lightning arresters, you would utilize the high pot adapter again, just like your high potting URD cable, you would essentially high pot the arrestor. So normally industry standard is about 20 microamps. Anything beyond that is considered a failed arrestor. So you can actually determine that by the display, how much leakage you have on that arrestor versus what's good or bad, basically a pass or fail. And then a DC cable tracer. So a moment ago, I mentioned we had a DC power supply out here. So that power supply, if you thread it on one of these probes, and I actually have it threaded on a second probe, and it's in my other cabinet over here, other three-phase cabinet, and we'll actually trace that URD cable. Again, it's de-energized, but we'll trace that URD cable over to this cabinet and determine which cable it is. So again, it's a device that you can use on URD or overhead to trace de-energized cable. So it's basically like ringing out a line, like the phone company does when they ring out lines. You're essentially ringing out a long run of cable de-energized to determine which one it is. So it's essentially de-energized phasing, so to speak. Okay. So again, I'll just show you real quick. This is the power supply here. It just threads on the end of the probe, and I have it on the second probe. I have a cable going to ground, and I'm looking for that potential on a cable over here. So what we'll do is we'll start backwards in sequence, and we'll start with the DC cable tracer. Since we already have that hooked up, I can easily start there, and then we'll just find it on this three-phase cabinet. Again, over on our other three-phase pad mount, what I have connected is I have a second probe connected to the DC power supply, and it's attached to this primary cable. And I'm going to cheat a little bit here. Normally, you guys wouldn't have any tape maybe in the field, so you really wouldn't know what cable this is, but it's attached to this cable we have taped orange. So this cable is already stood off. It's on a feed through, okay? And I'm going to use the meter probe with a bushing adapter and find that potential, okay? So normally in the field, again, you may not have any nomenclature. You may not have any tape on this primary cable, but you need to find this primary cable. All you know is you have it stood off, de-energized, and now you kind of have to sort through the cables, okay? So I'm going to use this meter probe. I'm going to attach my bushing adapter to it. And since this is a 100-volt DC power supply, I can put this meter in the 2 kV switch position. Get Ryan to zoom in on the back. I'll just flip it in the 2 kV switch position. I'm going to get Ryan to zoom in on this real quick. And again, as I mentioned, there's one of two options to do this. So I can connect another second probe to ground, and this is somewhat of a permanent fixture. We call it a somewhat of a permanent fixture. A lot of utilities, what they'll do is they'll order an accessory to the second probe, and they can attach any type of clamp that we manufacture to that. So I have one of our 3/4 C clamps attached, adapted to the second probe to ground. Or you can use this, which is just an alligator clip. Now, as I mentioned earlier, if you go with just an alligator clip to ground like this, you have to keep in mind that you have a ground potential right here at this cable. So if you're doing this on an overhead situation, what you can run into is if I have a ground right here and I'm working from a stick and I overshoot and go to the conductor, you have that ground potential. That's not a very safe method, obviously, right? Because I have no protection in this circuit, no second probe. If I use this scenario where I have 25 million ohms in series and I do that same thing, I attach to my meter probe and I overshoot and I go to a phase, I have some protection built into this circuit. So keep that in mind. We encourage people to use a second probe whenever they do this, whether it's underground or overhead, obviously, just because it's a safer method. And again, you can utilize any type of clamp. You know, some utilities, they'll order our flat clamps and they'll attach it to a steel structure. They'll have a 50-foot cable and they'll go up in a bucket and they'll check for induced potentials and see exactly how much induced potential they have on those conductors before they put grounds on it. Again, extremely accurate. It's going to tell that alignment exactly how much potential is on there. So within 1%. So what I'm going to do is I'm going to go ahead and use this scenario with my second probe. And again, I'm going to look for that potential. All right. So since we know it is this cable, all right, so we see 66 volts. Thank you, Brent. We see 66 volts there. All right, so what that means is again, I'm applying that 100 volts at the far end over here, and I'm going to find roughly half of that. So I'm splitting that potential in half with those resistors, those probes. So that's why I see the 66. Okay, so again, I'm ringing out this de-energized underground primary line. Okay, so that is the last one on the list that we just talked about. That is the DC cable tracer. All right, so that's one. The lightning arrestor, we don't actually have a bad lightning arrestor here. We do have one up on the pole, so we won't be able to actually demonstrate that, but we will high pot the URD cable. So the one right above it, where we high pot the URD cable, again, you're essentially high potting the arrestor. So I'll just kind of reiterate again what the method that you would do that. You would essentially pull the stinger off the top of the arrestor. You would take the meter probe with a high pot adapter. I'm going to leave this bushing adapter on here just because I'm going to high pot this cable in just a second. But you would take the meter probe with the high pot adapter attached to it. You would go to your energized source, and you would take your second probe and go to the top of the arrestor where you just pulled off that stinger wire. And that display would tell you if that arrestor was good or bad based on the leakage in that arrestor. Okay, so it's exactly like you're going to high pot cable. So if you're used to high potting using a traditional phasing meter, high potting URD cable, that's how you would high pot an arrestor. So we're going to go ahead and high pot this exact same cable we just put the DC cable tracer on. So again, with high potting primary cable, as I just mentioned, I want to always put my high pot to the energized source. So we do commonly get the question, does it matter where you put the high pot adapter? Should I attach it to the meter or should I attach it to the second probe? And the answer to that is it doesn't matter. I just get used to attaching it to the meter just out of habit, and I'm consistent with that. So whichever way you're more comfortable, whichever way makes more sense, you can do it either way. Just again, make certain that whichever probe you attach the adapter to, you always take that to the source. The high pot always has to go to the source cable. So since we're high potting roughly 13/8 phase to ground, I want to flip this switch to the 20 kV switch position. Okay. And I'll just show everybody that real quick. Get Ryan to zoom in on that. All right, 20 kV switch position. And I'm going to go ahead and put this to my source and my second probe to the cable. So I'll put my second probe on the de-energized cable first. And then again, I want to take my high pot adapter to my source. Now my source, if you'll notice, I have to cover off all three of these phases over here. So I can use any one of these cables as my source cable. All three of these are energized. So I can just pick one of the three. I'll just go ahead and pick the white. All right. So that number spiked up and then started going down. I don't know if everybody saw that or not, but I'll do this one more time just for the sake of everybody seeing that number. So this number has gone down to 0.13. Okay. So this cable is, I don't know, maybe roughly about 100 feet long or so. So this cable will have some amount of leakage on there. But again, remember, 1 microamp is 50 volts. So that's extremely low leakage on this cable, right? Because it's 0.13. So if it's in a 20 kV switch position, that means that this is roughly 130 volts or thereabouts, right? So that's not very much leakage. So extremely low leakage. This cable is relatively new also, and it's short. So again, the older the cable, the longer the cable, you know, you may have much higher leakage. To de-energize this, remember I just put the potential on the de-energized cable, but now I want to take that potential off that de-energized cable. So we have to do essentially just the opposite. I have to pull this meter off the source. Now the source becomes the cable I just energized. So I'm going to take my meter probe back to this cable I just energized, since it's my source cable now. Keep having everything sideways. And my second probe, I want to take it to ground. So watch whenever I touch ground with this, watch that number. You should see it spike and then go down. So it went almost to 1 kV and then went down to nothing. Okay. So again, with the accuracy that built into the tool, you can see exactly how much potential is on it once you de-energize it. So you know you fully de-energize that primary cable. Now it's safe to handle. Okay. Then I want to take this meter probe again and put it on my source. And I'll get Ryan to kind of focus in on this housing before I insert it, just so you see that number kind of jump up. Ready? See that number jump up? So it jumped up around 5 kV, you know, almost 6 kV, and there it goes right back down to near 0. Okay. So you see that potential being inserted into that de-energized cable, and you should see that number bleed off. Now, if this cable has a bolted fault, in other words, it's truly grounded, this number will be roughly 70% of phase to ground. Now, what does that mean? That means that it would be no different from essentially testing the high pot. So if I leave this high pot attached to an energized phase like this, and I take this second probe and touch the ground, you see that it's roughly about 10 kV thereabouts, right? And this is close to 14, it's 13.8 phase to ground. So there's your roughly 70% phase to ground. But remember what I mentioned earlier. I'm actually testing the high pot doing this. So I can verify that the high pot is a good accessory, a good adapter before I go using it. Okay. But that's what you would see on a bolted fault, is that number right there. That's what you should expect to see. If you had a high impedance fault, what you would see is this number may go up to some value. So like it's starting to bounce around. I'll get this number to bounce around a little bit. I'll try to do my best on this, but it's hard to duplicate a pinhole. But maybe it goes up, it goes down, it goes up, it goes down, it goes up. And see, basically what it's trying to do is it's trying to charge that cable up to some potential. Maybe it's 6 kV, 7 kV, whatever that number may be. And then it tries to discharge, or it does discharge. It actually blows through that little pinhole or high impedance fault, wherever that may be. You know, maybe it's to the concentric, whatever. It blows through there, discharges the cable. It tries to charge it back up. So it just sits there and oscillates back and forth. So you'll see that number bouncing around, up and down, up and down. That's a high impedance fault. So it's essentially one of three scenarios. Whenever you're using this tool to use it as a high pot adapter or a high potting meter, is you'll see a low number representing a good cable, a high number, constant high number representing a bad cable, and then maybe a high impedance fault, like, somewhat what I was trying to duplicate just a moment ago. And again, that's still a bad cable. So those are one of the three scenarios that you'll come across. So again, we want to discharge this cable. So I want to take my high pot adapter back to my source, which is the cable we just energized. And then I want to take my second probe and make sure I attach that to ground again. To de-energize, I can watch that scale. I see it jump up a little bit and go right back down to 0. Okay, so I know that's de-energized. Again, the PD50 will operate exactly the same. No difference whatsoever, with the exception of the scale. So what I mean by that is since the PD50 is a higher rated device, instead of having 25 million ohms per probe, it has 50 million ohms per probe. So the number, instead of seeing 50 volts for every microamp of leakage, you see 100 volts for every microamp of leakage. Okay, so that is the only difference that you'll notice. But as far as the operation of the tool, it operates exactly the same as what we just did here. High pot tester is exactly what we just did, testing the high pot adapter itself. That's a high pot tester. Again, that's a single use tool. With other manufacturers, I can use a PD25 to actually test the high pot. So if I want to use the PD25 as a phase sequence rotation meter, and again, I can do this in secondary applications or primary, it doesn't matter. And the first one I'm going to do is secondary. But the only adapter that you need is this little device right here, this little phase sequence adapter right here. And this connects in series with the interconnect cable. So I have another meter sitting here that I have some low voltage adapter probes attached to it. And essentially what that is it just covers up the larger surface area of the cone tip. It insulates that. So if you are using this tool, maybe inside a secondary disconnect, zoom back. If you're utilizing this tool in a secondary disconnect, you don't want that large surface area to maybe cross connect, because those little fuse holders, whatever it may be in there, it is pretty close proximity. So we do have this adapter, it covers that. You have a much smaller surface area to work with here, so less likely to cross connect with anything. And again, all I want to do is just plug this adapter in series with the interconnect cable and take my reading. So if I'm going to test this 12208 right here to determine the sequence, what I want to do is pick any two of the three phases. It doesn't matter which way you start this, just pick any two of the three and take a reading and then swap your connection. So in other words, if I start from left to right here and take a reading, and then I swap and take another reading, whichever one of those tabs, the secondary tabs right there, had the higher reading is the leading phase. Okay, so let's just go ahead and do that. So I have it in the 2 kV switch position. Again, this is 12208 3-phase, 2 kV switch position. And keep in mind while I'm doing this, the single-use device that we're referring to, this counterclockwise, clockwise rotation meter that you're probably using now, is a secondary rated tool. This is a primary rated tool, right? So I'm in a primary cabinet. Yes, I do have a secondary side to it, but this is a primary rated tool. So again, additional safety built into this. But I'm going to take my reading I'm going to pick the left one and the center one, and I'm going to take my reading here and see what I get. So I get a 95. I'm going to get Ryan to move the camera. Okay. I'm going to swap the two and take a reading again. And I get a 116. You see that, Ryan? Okay. All right. So this X2 bushing had a higher reading than the X1 bushing. So that phase is leading. All right. So what I would recommend, if you ever utilize this tool versus the tool that you're using now, I would recommend that you connect your tool now that you're using to the same scenario. And if that tool said counterclockwise, then from that point forward, if your phases went from right to left using this tool, that represents counterclockwise. So you would have to associate it with the tool you're using now, because some of those manufacturers may differ a little bit as far as clockwise, counterclockwise. You would just have to compare this to the tool you're using now to get that designation of clockwise, counterclockwise. But this is telling you the sequence left to right, right to left. So you'd have to, again, compare that to the counterclockwise, clockwise. All right, so that's on secondaries. Now on primaries, again, we mentioned a moment ago, this is, again, where this tool really stands out, because there's no other device that will do that. As far as a traditional phasing meter, there's no other device where you can do your phase sequencing on primary conductors. Just to demonstrate that you can do it, it's not going to hurt the device. I'm actually going to leave this in the 2 kV switch position. Let's just say that, again, I'm utility, I'm a lineman. I came out here, phase sequence on my secondaries. I forgot to change the switch, you know, but I went ahead and put it in these primary bushings. What's going to happen to the device? I'm going to leave it in the 2 kV switch position. So let's see what happens to the tool when I do that. Again, I'll just pick any two of the three. It doesn't matter which one it is. All right, so it just shows a 1, right? Okay, that's the display it'll give you if it's the screen is overloaded. In other words, it's just out of range. It's just going to show you a 1 if it's out of range. All right, so that's all it's going to do, is just do that. So I want to flip this to the 20 kV switch position, and let's see what it does in that switch position. I'm trying my best to yank this microphone off me. Remember what this is: phase to ground and phase to phase. Okay, so that's 13,900 roughly. 10,700. All right. So my H2B is leading my H1B, right? So I got 13,000 here, roughly 10,000 here. So my sequence is from bottom to top, if you want to say that, right? Or left to right, but most people would say from bottom to top. That's my sequence. Taking readings that could be affected by the way the cord is laying. So in other words, whenever I was taking this reading right here, and I'll show this again in more detail in just a moment when I talk about the true RMS feature, but this cord is laying on the ground, right? It doesn't matter where this cord lays. This cord can be laying on the ground. It can be touching the cabinet. It doesn't interfere with the reading. So even though these aren't accurate readings because I have that phase sequence adapter in there, you're still concerned with the readings because I want to know which phase is leading what. I want to see which one has the higher reading. But it's consistently going to be accurate as far as telling me which one has the higher reading, regardless of how this cable is laying. Okay, So it doesn't, you know, again, it could touch the cabinet, touch the ground, doesn't matter. Doesn't matter how long this cable is. I can still perform this function. All right. So that's your phase sequence, you know, your phase sequence rotation meter. Again, single use device. Some utilities, they found that they can actually replace 10 single use items utilizing this tool with several adapters. So just keep that in mind as far as saving room on your truck, simplifying the ordering process, saving a lot of money, obviously, because you're just buying one tool with some adapters versus several different tools. So it simplifies things tremendously. All right, so next on the list is the line regulator neutral detector. Now, what we have here is a regulator, 23.4, 13.8 phase to ground. And I want to determine if I'm in step or out of step. So I want to see a difference in potential is what I'm looking for. So right now, I have less than 10 volts. So if I take this device and I raise it a step, I want to see what the difference of potential goes to. And it goes to 70 volts, 75 volts. Okay. So there is the in step, out of step. I'm verifying that the light in this regulator, the display, the neutral light in this Cooper controller is actually correct. So I want to make that light is correct, or the dial. So I'm down here on the ground. This regulator is way up in the air. I'll get Ryan to show you where this regulator is physically at. So it would be actually hard from somebody on the ground to see that dial on that regulator to see if it's in step or out of step. They would have to rely on this light inside the controller. And again, that's a little bit to do because what if the lights burn out? Again, what if it fails? There could be a lot of things going on there. So I want to put this tool in the 2 kV switch position. Ryan, zoom in on that. I want to put this tool in the 2 kV switch position for the best accuracy. And again, this is replacing a single use item. And we have this rigged up a little bit differently than what you would normally see in the field. We're in the process of still modifying our training yard. Normally this regulator would be down fairly low, like in a substation where you would just have the, you know, the line side bushing, the load side bushing. You can go to line or load, or you can go line to ground or load to ground. There's one of 2 ways to determine if your regulator is in neutral position. You can do it 2 different ways. I prefer just to go from your line bushing to your load bushing, straight across. Again, cable can touch the can. It doesn't matter. The accuracy is built into the tool. This can touch anything. It's not going to affect the accuracy of the tool. But you can do it again one of 2 ways. So this is a secondary method, a primary rated secondary method of determining if the light's accurate in this controller and if the dial's accurate on the regulator. Okay. So that's utilizing the tool as a regulator tester. All right. So next on the list, capacitive test point phasing. And I'm going to phase across these capacitive test points. And as I mentioned a moment ago, whenever you're phasing capacitive test points, you have to make sure the capacitive test points are actually good because they have been known to fail. Like I said, we actually have one in our yard that's actually failed on us already. And it's just a few years old. And you can just imagine in the field, 20, 30 years or however long, they could fail pretty easily. And I want to do this in the 2 kV switch position. Depending on the manufacturer, capacitive test points could have anywhere from 200 to 300 volts roughly. Again, if it's failing, obviously less than that, but you know, all the manufacturers are different, even the same manufacturer, and if they're different ages, could vary substantially. So in the 2 kV switch position, it's going to give me the accuracy in order to phase and test the capacitive test points themselves. So the first capacitive test point I'll touch here. And again, I just want to go to ground with that, 160 volts. Go to the next one, 357. I go to the next one, 354. Okay, that's one side. I go to the other side. Let me switch hands so Ryan can see a little bit better. Go to the other side. I have 370, 368, 367. Okay, so all these capacitive test points are very close together. All right. So if I go phase to phase, in phase, I should get some number less than that. And phase to phase, out of phase, I should get some number higher than that. So all those are roughly 340, 350, 360. There's phase to phase in phase and phase to phase out of phase. There's again my 366, 67. 370. But in phase, it's about 310. Okay, so that's your lower number. That's your in phase number. And if I move my second probe over here, you'll see that number go back up to your 360. 360. If I find that blue phase over here, since this one was 360, if I find that blue phase over here, 360, should be around 300, and there it is. That's my 312. So that's how you find your in phase number. Okay. So again, capacitive test point phasing. Verify that your capacitive test points are good. Phase to ground. And then go about phasing. You know, obviously we have our phases taped here, so we're obviously cheating a little bit. We know what's in phase and out of phase, but your reading will actually tell you. So your in phase number should be lower than your phase to ground and phase to phase readings. That number should always be lower. So again, you saw your 300-ish, roughly around 300. That number was consistently lower on all 3 phases in phase. Okay, that's your capacitive test point phasing. The next one is DC voltmeter. And again, I can use my DC adapter, my 100-volt adapter. So when we were ringing out the line earlier, and this would be no different from, again, checking batteries in a substation. You know, if you want to use your truck battery as your known voltage source before you use the tool, you can do that. So you should see your 13 or 14 volts, whatever the truck battery is. I want to leave the tool in the 2 kV switch position since this is only 100 volts. So your DC testing, take that handle off. You should see that right there, Ryan. You see that okay? Yeah. All right. So there's roughly your 100-volt power supply. Now this power supply has inline, all these batteries are basically stacked. They're like little camera batteries in here. So again, the utilizing this adapter with the extremely high resistance, it pulls, again, just microamps. So this adapter will last an extremely long time, essentially the shelf life of the batteries, because there's essentially no current draw whatsoever using extremely high resistance like this tool right here. So that's your DC check. Again, you could check truck batteries, you know, any type of batteries in substations, anywhere you may have batteries. And a highline resistive voltmeter. So again, it's just an alligator clamp connected to the ground. I want to attach this meter probe to one of the primary bushings and see what my potential is. So again, highline resistive voltmeter. Some utilities use this with a 100-foot cable, 50-foot cable. Very rarely, if ever, they're going to use a short cable like what I'm about to demonstrate here, just because there's really no need to do that. Now I left that on the 20 kV switch position or 2 kV, one of the two. Again, that's my one. Again, just demonstrating it's not going to hurt the tool. It's just giving you a one, telling you it's out of range. Yep, left it into 2 kV. Okay, so 14,270, 280 volts. All right, so that again, that number is going to be within 1%. Highline resistive voltmeter. Again, using an alligator clamp on one end, cable, interconnect cable at any length up to 100 feet to your meter probe. So phasing and measuring secondary voltages in the 2 kV switch position. And I can do my phase to ground potentials or phase to phase. So if I go to ground on here, get my X1, there's my 121 volts. Get Ryan to zoom in on that. Go to X2, my 121 volts again. Try to get my glove out of the way. Try not to rip my microphone off at the same time. And the X3. Okay. All right. Phase to phase. Take phase to phase readings. Again, you can't phase if one of these is de-energized, so make sure they're all energized. There's my 211 volts. Right there. X1, X3, 211, 212 volts there. So that's my secondary meter there. Secondary phasing, secondary voltage readings. And again, that's more of the same with number 3. If you look at the list, because all your C&I voltages, that's essentially what they are secondary voltages. So those two are basically going hand in hand along with number 2. So number 2, those are true RMS readings that we just took. The 121, the 211, 212, true RMS, extremely accurate within 1%. And the phasing, your traditional phasing, you know, the traditional phasing here would be your phase to ground and your phase to phase. We can do all of our phase to ground, our phase to phase in phase, because again, just like with the secondaries, you want to make sure your phases are actually energized, because we get calls a lot of times, you know, the phases are funny, that doesn't read right, whatever the case may be. And the problem is it's actually de-energized, or they're trying to phase to an induced potential. So that's why their readings are funny. So keep that in mind. It always has to be energized. So if I go phase to ground here, about to do it on the wrong switch position because I already saw my 1. And since I am going to do phase to phase out of phase, remember this is 23.8, 23.9 roughly phase to phase. So I have to put it in the 25 kV switch position. But my phase to ground readings, so here's my 14,100. Get Ryan to zoom in on that, just so you guys can see that number. So 14,100. 14,100. And 14,100, okay? Now, notice I'm going to do this a little bit different here. I actually went using my second probe phase to ground. I'm going to go my meter probe with my second probe to ground. Okay, that may not sound like a big deal, but again, other manufacturers, you'll actually see a discrepancy in that reading. It won't be the same. So I'm just going to prove real quick that if I did go to the same phase, phase the ground this way, there's my 14,100. Roll over to 200 a little bit. So again, within 100 volts, within 1%. So I'm going to take this reading, phase the ground here, 14,100. Get Ryan to zoom in on that. I'm going meter probe to the energized source, second probe to ground. Make sure this one is hot. 14,000, roll over to 200. Okay, Ryan. And 14,100. All right. So all my phases are hot. Everything's good to go. Now I can begin phasing, in phase and out of phase. So if I pick any one of these three, if I already know this one's in phase because I have my red tape, I can cheat. But there's my 0 volts. Okay. There's my 0. If I go out of phase, there's my 24,600 volts. So everything's running a little bit high here. Obviously, there's no load on our training yard. My 13.8 is not really 13.8. It's 14,100, maybe 14,200, because it will round off depending on if it's high or low. And my 23.9 is a little high. It's actually 24,600. So everything's a little bit high, and we can see that using this tool. So that was my phase to phase, in phase, phase to phase, out of phase. If I want to see if the white's in phase with my white over here, I can verify that. There's my 0. And again, my blue should give me my out of phase, my 24,100, 700, I mean. Okay. All right, so that's number 1, and that's the underground. Again, overhead would be no different.